Okay. Polyatomic ions. Poly. Prefix poly, what does it mean? More than one, multiple, right? Atoms. More than one atom ion. So an ion made up of more than one atom. Okay? So a polyatomic ion is a group of atoms held together by covalent bonds with a charge. Without a charge, it's called a molecule. With a charge, it's called a polyatomic ion. A many-atomed ion. Now, I've studied your book. Your book's homework is going to have you draw these tonight. And I read your book, and your book does not teach you how to do it. Right? I don't know how they expect you to do it. Because the way you get a charge is by moving electrons around, right? So you're not going to know which electrons to add or which ones to take off. You start building it and you say, oh, and I have to erase some of these dots. Which ones do I erase? Or I have to add some dots. Where do I add them to? I don't know how the book expects you to do it. So we need to do the math. You can't build them directly. You need to use happy minus half divided by 2. And that equals the number of bonds. Now, because you've got a charge, the number of electrons is different. And the number of electrons you have is going to be different. Your have number is going to be different. If you've got a charge, you've changed how many electrons there were. If you've got a positive charge, you've lost electrons. If you've got a negative charge, you've gained electrons. So if you've got a positive charge, there's electrons missing from your picture. If you've got a negative charge, you get to draw extra dots in your picture. So it's going to be negative. Negative has extra electrons, so my have number is going to be bigger. If I have a negative 2 charge, I'm going to add 2 more electrons to my have number. It's got a positive charge. I'm going to have to take electrons off, because that's how you make something have a positive charge, is you lose electrons. Now, we're not going to be able to say specifically which atom gained or lost electrons. All we'll know is that there's extra or missing somewhere in this big piece. So to do that, we have to say the whole big piece has a charge. To do that, we put that whole big picture in brackets. Brackets are the square ones. And then write the charge outside the brackets. So if I put a 2 minus outside the brackets, that means someplace inside these brackets, there are 2 extra electrons. Or if it's a positive 3 outside the brackets, it means somewhere in here there are 3 electrons missing. We don't know which ones they are, but we know 3 are missing. Okay? So let's draw a few. So the first one we're going to do is NH4+. This is called the ammonium ion. Now for right now, we're learning how to build atomic ions. When it comes to writing the names and formulas for compounds, though, there'll be a list of polyatomic ions you're going to have to memorize. Okay? You don't need to memorize them now, so we're not going to worry about that now. Memorize. Because chemists talk about it all the time. Okay, ammonium is what this is called, NH4+. Okay, let's do the math. Because it's got the charge, we need to do the math. So happy and have is what I got to worry about. And I need to worry about nitrogen and 4 hydrogens. Okay with that? Where I got all those numbers from? 1 nitrogen, 4 hydrogen. The happy number for nitrogen is 8. It'll look like a noble gas if it has 8. The happy number for hydrogen is 2. but there are 4 hydrogens. So I'm going to have to multiply that by 4. So when I'm done, the total number of dots it would take to make this happy is 16. The have number. How many of those 16 do I have? Well, nitrogen has 5. Hydrogen has 1. And there's 4 of them. So that's 4 more. And now I have to deal with the charge. How do I make something have a positive charge? You lose an electron, right? So I'm going to have to lose one of these. I got to subtract 1 because of the charge. Okay, that's where I got all those numbers from. We know how to do valence electrons. We know how to read the subscripts, so we know where all the numbers are coming from. Okay? Because there's 4 hydrogens. Because hydrogen has 1 dot. Hydrogen has 1 dot, wants 2. Happy with 2. So hydrogen's have number is 1, its happy number is 2. Nitrogen has 5. It would be happy if it had 8. So those are just the number of valence electrons. Right. So 5 plus 4 is 9, minus 1 is 8. And 16 minus 8 divided by 2 is 8 divided by 2 is 4 bonds. What does that tell me about this ion? Well, there's 5 atoms. What's the fewest number of bonds I could get away with? 4. How many bonds do I have? 4. So that's going to tell me that these are all single bonds. Okay? These are all single bonds. Because the way to hook together 5 things is to use 4 bonds. I've got 4 bonds to put in, so they're all going to be single. So I put them in. So I put in the 4 bonds. Then I make sure everything looks like a noble gas. Well, each of the hydrogens has 2 electrons because it's got 1 bond. The nitrogen has 4 bonds, that's 8 electrons. It looks like a noble gas. So everybody looks like a noble gas. And what I've drawn is 8 valence electrons, which was the number I had to work with. So I've got the right number of valence electrons. I'm only missing one thing. We lost an electron. Did I lose it from that hydrogen? Can I put that plus sign there? Did I lose it from that nitrogen? Can I put the plus sign there? Do you know? We don't know, do you? So that's why we do brackets with the plus sign. And that's the structure of the ammonium ion. It's got 4 hydrogens hooked to the nitrogen. You'll notice that nitrogen has broken the rules about how many bonds it made. And it can break those rules because we changed the number of electrons. Remember we said nitrogen makes 3 if possible. There was no way for it to make 3 this time. Hydrogen makes 1 all the time. Everything other one is our first try to put the right number in. Yeah. Let's try another one. This is the sulfite ion, SO3 with a 2- charge. Sulfite. It's what they warn you about on dried fruit. Sometimes they use sulfite as a preservative. So if you go buy dried apples and they're not brown, they use some sulfite as a preservative to keep them from turning brown on you. So, the math. So I got to worry about 2 things. How many to make them happy and how many they have. And I've got to worry about 2 kinds of atoms. The sulfur and the oxygen, and I have 3 oxygens. The happy number for sulfur would be 8, because it's 8 for everything except hydrogen. The happy number for oxygen would be 8. But there's 3 of those oxygens, so 3 times 8 is 24. So the total number to make it happy, if I just filled everything up, would be 32. The have number. Well, sulfur's in group 6A. It has 6 valence electrons. Oxygen is also in group 6A. It has 6 valence electrons, but there are 3 oxygens. So 6 times 3 is 18. Added onto that 6 is 24. But I've got a charge. I got a 2 negative charge. How do I make a 2 negative charge? Add 2 electrons. So I'm going to have to add 2. So my have number is 26. If it was neutral, it'd be 24, but it's got 2 extra electrons, so it's 26. So 32 minus 26 divided by 2 is 3. 3 bonds. 3 bonds and 4 atoms. What does that tell me? They're all single bonds. Now, sulfur and oxygen are places that want to make 2 bonds. But when you see a polyatomic ion like this, where it's got a bunch of oxygen, that first element's in the middle, the other ones surround it. Okay? That least electronegative one is in the middle. You notice oxygen is probably going to be the most electronegative one when that happens. So, sulfur bonded to 3 oxygens. Now I fill in and fill in all the dots. So the sulfur needs another pair because it's only got 6 electrons around it. All the oxygens have 1 bond, so they each need 3 more pair. And it won't let me draw the pair on the one on the left. I'm drawing it, and as fast as I draw it, it erases it. I draw it right here, and oh, it stayed that time. All right. Oh, it erased now. You can see I'm drawing 2 dots there, okay? I'm fighting it disappeared now. It doesn't let me write in this little area for some reason. I don't know why. Okay, now everybody looks like a noble gas. Now I want to count to check that I've got the right number of dots. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Oh, that's wrong. Oh, because these 2 aren't here. I need those 2 on top to get me to 26, the ones I can't draw. Because my have number was 26. So there's really a couple of electrons above that oxygen, right? All right. And I need to put, it erased it on me, so you'd have to put brackets and put a 2 minus. Right? Put brackets, because you don't know where the extra 2 electrons are. Can you tell? And then final one, Cn minus. That one's called cyanide. Smells like almonds, then you die. Actually, wild almonds are poisonous because they're full of cyanide. Okay, but people noticed, hey, there's an almond tree that all the birds are eating at, and they're not dying. Maybe we can eat those almonds, and that's how they got the genetic one that didn't, had the flaw that didn't make the cyanide. Those are the almonds you eat, but that almond scent is cyanide. There's still a little bit of cyanide in almonds, not enough to hurt you, but enough for you to detect by smell. So the scent of almonds is cyanide. So don't eat wild almonds. Okay, Cn minus. So how hard could that be? Well, it makes your nerves stop working. You fall on the ground dead. All your nerves stop working, so you don't breathe, you don't think, your heart stops beating. you just fall down on the ground. Okay, so happy and have is what I have to worry about. And I'm doing the math because they gave me a charge. I got to worry about carbon and nitrogen. Both of those would be happy with 8. So that's 16 for my happy number. My have number, carbon has 4, nitrogen has 5, and it's got a charge, so I have to add 1. That gives me 10. 16 minus 10 divided by 2 equals 3 bonds. 2 atoms and 3 bonds. The fewest I could get away with would be 1 bond, right? But I have to put in 3. So I got to make that a triple bond. And then I have to fill everything up. The nitrogen has 6 electrons, so I need a pair next to that nitrogen. The carbon has 6 electrons next to it, so it needs a pair as well. Now, check to make sure we got the right number of dots. 2, 4, 6, 8, 10. My have number was 10. There's an extra electron in here someplace. Everybody see where it's at? Nah. So, you don't have to put the 1, but it makes it, you don't have to put the 1, but it makes it easier for me to see when I write it there. So I need that 1 minus. The brackets and the 1 minus are about, there's an extra electron. So, everybody see how the math, does that help you with the math better? Okay, we're going to keep doing math today, by the way. So we're going to do lots of examples where the math works. Okay? I gave you the ones you didn't need the math right away. The ones you need the math to come up later. Okay. So the next topic is actually related to the one we just did, and it's called resonance. Heard the word resonate before? What does resonate mean? When something resonates. Okay, resonate is kind of like a wave that just keeps going back and forth. Okay? That's what resonating is, a repeating wave. Now, resonance happens. Resonance happens when there's more than one dot diagram with the same connections, and I mean the connections between atoms. So what I'm saying is, you've got the atoms all in the same order, and you have your choice of where the electrons can go. So when you do the math, and the math says you have to put a double bond in, and you have your choice about where that double bond goes. It says you need extra bonds, and you have a choice, and it doesn't matter which one you pick. The atoms aren't going to move around based on where you put that double bond. The example we're going to use here is going to be a polyatomic ion. This one's called nitrite. Nitrite is the stuff they warn you about on bacon and hot dogs. Nitrite's a suspected carcinogen. Okay. So now they make bacon without any added nitrites. Okay. But it's not any, they don't add nitrites. They add beet juice, and beet juice has nitrites in it. It's just got just as many nitrites. The no added nitrite has just as much nitrite. Okay? But it's what gives the distinctive flavor. Without the nitrites, it tastes really different. Okay? So let's do NO2 minus. Let's draw its structure. So NO2 minus, nitrite. Math? Happy? And have? And I got to worry about a nitrogen and 2 oxygens. The nitrogen would be happy with 8. The oxygen would be happy with 8. There are 2 oxygens. So that means the oxygen would take 16 added on to the 8. My happy number is 24. Everybody okay with that? Have. Nitrogen is in group 5A, so it has 5. Oxygen is in group 6A, so it has 6. But there are 2 of them. So that makes it 12. And it has a charge. To get a 1 minus charge, I would need to add 1 electron. Look at that. Okay. So 5 plus 12 plus 1 is 18. 24 minus 18 divided by 2 is 6 divided by 2, which is 3 bonds. As I said, if it's got 1 atom and a bunch of oxygen, that 1 atom goes in the middle. Everything else is hooked to it. So I'm going to hook the N and the O together with my single bonds. Now, where does the double bond go? Does it go here? Or does it go there? Am I going to have to move the atoms around? Okay, I have to fill in all the dots, right? Oxygen, nitrogen needs a pair. This oxygen needs 3 pair. That's 2, 4, 6, 8, 10, 12, 14, 16, 18. So I got the right number of dots when I fill it up. So I've put in all my dots. Okay. So, the chemist asked, which one is it? They said, no, it's not either one. It's really what happens is this pair of electrons hops in and makes a bond here, which forces this pair of electrons to go over there, and the electrons just bounce back and forth. Or I can bring these back and those back, and I'm back to where I started. That just moving the electrons can just move back and forth. I said, that makes sense. That's why they called it resonate, because it bounced back and forth between the two. So that's why they called it resonating, because they thought the electrons, notice I put in the phrase, they thought that the electrons moved back and forth between those 2 spots. Okay? But then they got some data. First of all, they knew that double bonds are shorter than single bonds. That means no matter which of these 2 it is, no matter which one, I would have 1 short bond and 1 long bond. If it's this one, the left-hand side is short, the right-hand side is long. If it's this one, the left-hand short is long, the right-hand one's short. Make sense? When they measured the actual bond lengths, all the bonds were the same length. You didn't have 2 different length bonds. All the bonds were the same length. Oh, then it can't be this. Because if you got this, one's long and one's short. If you got this one, one's long and one's short. Okay? The length that they were both the same length, the length was longer than a double bond, but shorter than a single bond. The bond length was in between the length of a single and double bond. So what does that mean? That means it's got two bonds that are the same. Kind of like a mule. With a mule, you put together a donkey and a horse, and you end up with something that's bigger than a donkey but smaller than a horse. Well, that's what we're doing here. We're going to put together the single and a double bond and end up with about 1.5 bonds on each side. Now, what we really want to draw is this. One and a half bonds. Okay? The problem is fill in the rest of the dots. You can't fill in the rest of the dots. So the problem is not with nature. The problem is with our bookkeeping system. That we don't have a good way to draw this. Okay? So what they do instead is they put a double-headed arrow in between them and to say that it's neither one of these, it's actually in between these two. So the way you indicate is you draw both and you put a double-headed arrow in between. Now I'm missing something from my pictures. I'm missing because these things had a charge, didn't they? So the nitrite had an extra electron and we can't see where it's at. Right, I need to go back and put those brackets on. So the brackets are about charge. The double-headed arrow is about resonance. Okay. Yeah.
Does it make a difference if I write it like that?
You want to show them separate, yeah, because the brackets means it's all together. Okay. So you want to draw brackets around each one of them. And I understand what you're doing, but we want to emphasize that they stand alone. That those are the extremes. The real thing's someplace in the middle. So our problem is we don't have a good way of describing this. It's not that nature's complicated. There really is about 1.5 bonds. Our simple method of describing it just doesn't do a good job. Right? Because we know these aren't what they really look like. We're just talking about how they're connected. And we don't have a good way to write 1.5 bonds. We'll deal with it later and see what's really going on. Okay. Let's try it with another polyatomic ion. This one, CO32- is called carbonate. It's what gives your soda its carbonation. Okay. So, do the math. Got happy and have for 1 carbon and 3 oxygens. The 1 carbon is happy with 8. The 3 oxygens are happy with 8, and 3 times 8 is 24. Or I can just say, hey, I got 4 8s, that's 32. Okay, have, carbon has 4. Oxygen has 6. There's 3 oxygens. 3 times 6 is 18. That 2 minus means 2 extra electrons. So I got to add 2. So 2 plus 18 plus 4 is 24. And 32 minus 24 minus 24 divided by 2 is 8 divided by 2, which is 4 bonds. Everybody okay? 4 bonds, 4 atoms. What does that tell me? Okay, it would take 3 bonds would be enough to hook them all together, so I need a 4th bond. That means I've got to put a double bond someplace. So Carbon is hooked to oxygen and oxygen and oxygen. That's the 3 bonds. Where does the 4th bond go? Does it go here? Or does it go there? Or does it go there? I got 3 places that double bond could show up. I got to fill in all the dots. The single bonded oxygens get 3 pair. The double bonded gets 2 pair. And I'm going to redraw that last one because I ran out of space on my screen. We've all seen the math, so I should be able to do. Carbon has got its 8, so it doesn't need any extra dots. So single bonded oxygens get 6 dots. Double bonded get 4. There's no sense of counting all of them, but I should be able to count one of them to make sure I got the right number. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. My half number was 24. Now, each of these has 2 extra electrons, and you can't tell where they're at, so you put brackets around each of them. And put a 2 minus up top to say they're all 2 negative. And then to say that they are resonance structures, you put double-headed arrows in between. Now on this one, when you measure the bonds, it's longer than a double bond, but shorter than a single bond, but it's closer to a single bond than the other one. That this is about 1 1/3 bonds. That this extra bond actually goes on all 3 of the oxygens. We're going to have to find a way for that to happen. Okay. So how do you know if there's resonance? Draw the diagram and see what happens. The only way to know if there's resonance structures was A, read the question that says draw resonance structures. You probably are going to have them there. But B, when you have that choice of where that double bond goes, and it doesn't move the atoms around. Now, resonance, the fact that you have lots of places to put those electrons that are stable, makes that whole molecule stable, that whole group of atoms stable. So that's one of the reasons why polyatomic ions exist, is oftentimes they have resonance structures. And the more ways I can make it stable, the more likely it is to be stable. Does that make sense? So resonance gives you stability, and it's the resonance that makes it so those polyatomic ions last. Now, if you draw a structure and something's got the wrong number of bonds, you want to check to see if you have a choice of where that extra bond can go. So we'll do it one more time. And this time we're going to not do, this is not a polyatomic ion. How do I know it's not a polyatomic ion? There's no charge. Okay? This is sulfur trioxide. Okay? It's a poisonous gas. Okay? Sulfur trioxide. So let's try sulfur trioxide. I'm going to sulfur and 3 oxygens. Happy is 8 for both of them. So that's 4 8s, so that's 32. Oops, I skipped a step. Everybody okay with that skip step? 4 8s is 32. The halve number is 6 for each one, but there's 3 oxygens. That's 18. Do I have to add or subtract electrons here? No, because it's neutral, right? So, oh, so 18 and that's 24. 24. 18 and 6, 24. Yeah, because if you'd subtracted 18, you would have had to make more bonds than there are atoms, and that's they're not. You wouldn't be able to have any way of making it that with that many bonds, because 32 minus 24 is 8 divided by 2 is 4. I have to put 4 bonds in, so I take the sulfur and hook on my single bonds, and have my choice of where that double bond is going to go. So it's at this point right here that I recognize that it's got resonance structures. Okay? Because I get to this point, I've got my 3 bonds, and I say, well, I can put that double bond any place. Does it make a difference where I put it? If it doesn't make a difference, you need to put it all of those places. And fill in lots of dots. Double bonded oxygens get 2 pair, single get 3 pair. And I could count this, but I just counted CO2, which looks exactly like this, and it was 24. Oh, it all disappeared on me, sorry. It just disappeared. So we end up with does it matter what order you put the resonance structures in? As long as you have the right number of them with the bonds in the right places? Okay. Do I need brackets? Don't need brackets because it doesn't have a charge. But I do need double-headed arrows to say these are really 3 views of the same molecule. Okay? The real molecule is someplace in the middle. That electron is really distributed all the way around that sulfur to all the oxygens. Now, you say, well, isn't everything, every time you do that, isn't that going to make everything an isomer? Well, here's a quick little one. If I had a compound with 4 carbons and everything else was hydrogen, and I went to put in a double bond, I have 2 places a double bond could go, either at the end or in the middle, right? And if I fill in hydrogens, as many as they can take, this is going to make it C4H8. But these two are not, these are not resonance structures. Because more than just the bond moved. This end carbon had 2 hydrogens, now it's got 3. This one over here had 2 hydrogens, now it has 1. Hydrogens moved around. These are not resonance structures. These are completely different chemicals. Behave differently because that double bond's in a different place. We'll practice some tonight and we'll talk more about that tomorrow.